Okay? And also interesting thing is, for example, this is cochlear activity, meaning that how much cochlea is activated due to the signal. Okay? For example, when you have a signal that only activates the cochlea this amount, okay, this amount, then you can hear 250 hertz, and then 500 hertz, and you can hear this amount, this signal. But it's not possible to sense at the lower frequency. So depending on the amplitude, right? So due to this kind of nonlinear behavior, our ear has many interesting characteristics. For example, masking effect, or cocktail effect, and so on. And we will have a chance to experience those kind of effect next lecture, okay, using some demonstration. Okay, but at least using this picture, we can say that, oh, our ear sense the pressure is rather differently than we expected, right? So when we have a sound pressure magnitude has to be scaled somehow related with our ears. Pressure magnitude. And the frequency content of pressure. Frequency content of pressure. In other words, lowest frequency we can hear and highest frequency we can hear. The lowest frequency we can hear is known to be 20 or 40 hertz, and highest frequency we can hear is known to be 20 kilohertz. So range of frequency is very broad. In other words, it's not possible to scale this frequency using linear scale. 20, 40, for example, 60, 80, 100, 120 to 20 kilohertz is really boring, right? Right? And the magnitude scale of sound pressure has a big dynamic range. In other words, we can hear very small sound and a very big sound. You can hear this kind of noise, and you can hear, for example, if Kang Dong-soo shout, sing a song, right? You can hear it. You can hear even louder sound, as well as you can hear very small sound. So this scale has to be somehow scaled by some references, right? So we scale this magnitude using 20 log 10 P reference to P average. P reference is reference pressure, that is 20 micropascal. Very small sound pressure, 20 micropascal. Is it magic number, 20 micropascal? 20 micropascal is the sound pressure that normally young people can hear. Okay? So let's take that as our reference sound pressure. Okay? Because sound pressure like 2 Newton, 2 Pascal absolute scale does not really provide us some meaning. So we take sound pressure with respect to the sound pressure that we can hear, minimum sound pressure that we can hear. Okay? Another reason is the range of sound pressure we can hear is so big as we see in frequency scale. So we need to use log scale. And also we need to use log scale in frequency scale too. Okay? So that's why we use octave scale for frequency scale. Octave scale means simply I have frequency band, and octave scale means F2 is simply 2 times F1. Okay? So in musical notes, when we have O, 1 octave down would be O, that is 1/2 of the frequency I just shouted. I don't know whether it's correct, but okay. The center frequency of this octave scale is simply geometric mean between F and F2. That means F2 divided by F0 has to be same as F0 divided by F1. Therefore, F0 is right? That is octave scale. That is we call center frequency of octave scale. And the bandwidth of octave scale is about 70% of frequency that can be calculated. Similarly, we can have 1/3 octave band. 1/3 octave band is simply means that the F2 is F1 case. In general, we can have nth octave band, 1/3 or 1/6, 1/12, if you like.